This video is going to cover capacitance and dielectrics for Special Higher Physics 1B. We're going to get to capacitance very soon, but before we do that, we're going to start by considering oppositely charged plates. Here we have two plates. This one's charged to a charge of plus Q, and this one over here has a charge of minus Q. They both have area A. They're a distance d apart, so this is at 0, this is at d. And what we're going to start by doing is working out the electric field at a few different points. We'll work out the electric field here, the electric field here, and the electric field here. Now previously we've used Gauss's law to work out the electric field due to a single plate. So let's just quickly recap that. We have an infinite plate with charge density sigma, positive charges, then the electric field lines are all coming out of the plate here, out of the plate there. And Gauss's law forces us to choose a suitable surface. So let's choose a prism like this with surface area A here and surface area A here. You can see the direction for the surfaces. Here it's parallel to the electric field along this surface, it's perpendicular. Here it's parallel, here it's perpendicular. And so to work out the electric field, we use Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. And so the electric field is constant over these surfaces, so we have E. And now the only surfaces which are contributing are the two ends of our prism. And each of them has area A contributing. So this is 2A. And this is equal to the enclosed charge, which is this surface area A times our charge density over epsilon naught. So these A's cancel off and we end up with our electric field due to the one plate is equal to sigma over 2 epsilon naught. And it doesn't matter how far away we get, this electric field is constant. Okay, so let's start by considering this plate, this part here. Now, this has a charge density sigma is equal to minus Q over A, and this plate has a charge density sigma is equal to plus Q on A. So the sigmas have the opposite sign. So when we add the electric field contributing from this plate and this plate, we end up with 0 here. So out here, the electric field is 0. And this is because the electric field does not drop off with distance. This is assuming that these plates are very large. If the plates were small and our distance is large enough, then it's going to look more like a dipole, and so our electric field will resemble the dipole form more rather than 0. This is assuming very large plates. Now in between, the electric field from both the plates is actually acting in the same direction. So it's coming up out of this plus Q plate, and the electric field lines are going into this negative Q plate. So what we need to do to get the total electric field at this point is add the contributions from this plate and from this plate. And they are going in the same direction, so they will add. So we will end up with twice this electric field here. So E between plates is equal to sigma over epsilon naught. Now outside here, we have exactly the same arguments as outside here, and we have E is equal to 0. So now we've worked out what the electric field is between our plates, and given that these plates are big enough and the distance separating them isn't too large, this is a good approximation. We could also write this as Q over A epsilon naught if we wanted, as sigma is the charge density, which is Q on A. Now what we're going to do is work out the potential difference between these plates. So the potential difference is equal to the voltage at D minus the voltage at the plate located at 0, and this is equal to minus the integral from 0 to D of E dot ds. Now we've worked out the electric field between these plates. It's got this magnitude and it's going in the red direction here. We'll take a path ds going from here to here, so that's the direction of ds as well. So when we take the dot product, we just need to multiply these two things together. So working out what this integral is, we substitute in here. So we've got minus the integral from 0 to d of q over a epsilon naught ds. This is all constant, so we could pull it out the front and we end up with minus QA over epsilon naught times the integral from 0 to d of ds, so that is equal to d minus 0. And so this is equal to minus QD over A epsilon naught, and that's our voltage difference. So we've now got the voltage difference as a function of the charge on these plates. This brings us to our definition of capacitance. The capacitance is equal to the ratio of the charge stored on the plates over the potential difference between the plates. We don't need to worry about if it's a positive or a negative potential difference, because just switching our reference plate will switch that sign. So now in this definition, Q is the charge on one plate. So you have to have a positive plate and with charge positive Q, and a negative plate with charge negative Q on it. Now, what we can do is we can actually work out an expression for the capacitance in this case, because in this case we've got that Q over delta V is equal to Q over QD over A epsilon naught, and that is equal to A epsilon naught on D. So the capacitance for two parallel plates is given by epsilon naught A on D. Now, this capacitance is going to depend upon the geometry of the two plates. To have a capacitor, we always have a charge plus Q and a charge minus Q, but depending on exactly how the electric field is between those two charges, we will end up with slightly different expressions for capacitance. Let's have a look at another situation where we have a slightly different expression for the capacitance. Let's consider the situation where we have a hollow pipe of length L, and inside that we have a solid cylinder also of length L. Looking from on top, the inner cylinder has a radius A, and the outer cylinder has a radius B. The question is, what is the capacitance for this arrangement? And we've got a charge of plus Q on the inner cylinder and minus Q on the outer cylinder. So to work this out, we do it in exactly the same way as with the last arrangement. We work out the electric field between these two cylinders, and to do that we can just use Gauss's law again. So the integral of E dot dA is equal to the enclosed charge over epsilon naught. The charge enclosed within this cylindrical surface is given by plus Q over epsilon naught. Now the electric field is constant in this region. It's all the electric field lines are going out like this, and so we've got E, and the part of the surface that we need to consider is the part with the rectangular cross section. So that has surface area 2 pi RL. And so we have our electric field is given by Q over 2 pi RL epsilon naught. So now we've got our electric field. Now we can work out what the voltage difference is between the radius at A and the radius at B. So V is equal to the integral, negative of the integral going from A to B of E dot ds, and this is equal to minus the integral from A to B of Q over 2 pi RL epsilon naught dr, because we're going along a radial path, so this ds is dr, and so this is equal to minus Q over 2 pi L epsilon naught, and then we're integrating 1 on R. When we integrate 1 on R, we get log R, and this is at B and A. So we end up with Q over 2 pi L epsilon naught log B on A, because it's log B minus log A, which is log B on A. So finally, the capacitance is equal to Q over delta V. We've now calculated our potential difference between the point at A and the point at B, and so substituting in, we've got Q over 2 pi L epsilon naught, and that's on the bottom, and then it's times log B on A, and so this is equal to 2 pi L epsilon naught over log B on A. And that's our final answer. That's the capacitance of capacitors set up like this. We're going to consider one final example of a way to set up a capacitor. In this case, we're going to have a sphere with a charge plus Q, and then a hollow sphere with a charge minus Q on it. In this case, we'll get an electric field like this. And we want to work out the capacitance. So we do this in the normal way. We draw a Gaussian surface and we'll work out the electric field through that Gaussian surface. This is at radius r. The inner sphere has a radius a, and the outer sphere has radius b. So to work out this electric field, we have E dot dA is equal to Q enclosed over epsilon naught, and so we have E times the surface area, which is 4 pi r squared, as this has radius r, is equal to the enclosed charge, which is just the plus Q over epsilon naught. And so we have that the electric field is equal to Q on epsilon naught 4 pi r squared. Now what we need to do is work out the potential difference between the radius A and the radius B. So we've got that the potential difference is equal to minus the integral from A to B of E dot ds. And in this case, the path we're taking is along the radius. So this is equal to minus Q over epsilon naught 4 pi dr over r squared, where the radius is going from A to B. So integrating this, we have Q over epsilon naught 4 pi 1 on r from B to A. The negative sign has cancelled out with a negative sign in our integral, and so this is equal to Q over epsilon naught 4 pi B 1 on B minus 1 on A. So let's write this as Q over epsilon naught 4 pi, give it a common denominator AB, and it is A minus B. This is going to be a negative number as A is smaller than B. So finally what we want to do is work out the capacitance. The capacitance is given by Q over delta V. So this is equal to Q over this. So we've got Q. Now, because this is an absolute value, we're going to replace A minus B with B minus A because that's positive. And as we're dividing by this thing, we can put this thing on the top. So that's epsilon naught 4 pi AB. So the Q's cancel and we end up with a capacitance epsilon naught 4 pi AB over B minus A for a spherical capacitor like that one. Now let's just quickly consider what capacitors actually are. Capacitors are little circuit components which generally look like a little box on two legs. Capacitance is measured in farads. Named after Michael Faraday. Generally, when capacitors are made, they're made from two pieces of metal which are wound around each other. One's the positive plate and one's the negative plate. And surrounding this coil of wire is what's called a dielectric material. We'll be looking at dielectric materials very soon. Capacitors are used in circuits to store charge. Current cannot flow across a capacitor. If you get an electric shock from a circuit a while after it's been turned off, it probably means that there's a capacitor in the circuit. We can buy components called capacitors, but it's also possible for circuits to have capacitance without capacitors in them. So if you're working in electronics, sometimes you need to take this into account. Any two plates or two wires next to each other where you have a positive charge and a negative charge can act as a capacitor, and so this can affect the properties of the circuit. Now we're going to consider dielectrics. Dielectric materials are insulators. Generally, they increase the capacitance. They do this by decreasing the electric field between the plates of a capacitor. Let's start by considering what happens when we insert a piece of metal, which is a conductor between two plates, and then we'll consider what happens when we insert a dielectric. So if we have two plates like this, a distance d apart, and we insert a piece of metal with width b. Here we've got a positive plate, and here we've got a negative plate. Now we know that the charges inside the piece of metal are going to rearrange to cancel out the electric field within the piece of metal. So we'll end up with negative charges along here and positive charges along here. Now let's consider what's going to happen to the electric field here. Let's call this 0 and we'll call this distance d. We'll call this distance a, and then this distance will be a plus b. Now we know that the electric field between two plates is given by sigma over epsilon naught, and that doesn't actually change with distance. Now the electric field up here is going to be given by this as well, because this part can't actually tell if these negative charges are very close by or at distance d. It makes no difference. So the electric field in here is going to be given by this expression. The electric field inside the conductor is 0, as the charges have rearranged to cancel it out, and the electric field in this part is also going to be given by this expression. So let's now use the electric field to work out the voltage difference between our two plates. We know that our voltage difference is equal to minus the integral of E dot ds, and what we'll do is we'll split this integral into three parts. We'll do this part, we'll do this part, and we'll do this part. And so between 0 and a, we've got sigma over epsilon naught ds, and then we've got 0 in here, there's no electric field, so we can leave that out, and then we've got between a plus b and d, sigma over epsilon naught ds again. So just doing this integral, we'll pull sigma on epsilon naught out the front. This first integral, we've got a minus 0, and we've got a negative sign, and then in the second integral, we've got plus d minus a minus b. And so we end up with minus sigma, which is q over a epsilon naught d minus b. Whereas before we just had a d here. So we could actually write this as q d over a epsilon naught with a minus out the front, and we can write this as 1 minus b on d. So it's like the original delta v, but times by this factor here. So to get our capacitance in this case, C is equal to q over delta v, and so this is equal to epsilon naught a d over 1 minus b on d. So you can see the capacitance has actually increased because 1 minus b on d is some number between 0 and 1, as b has to be less than d. So for a metal, our dielectric constant would be given by 1 over 1 minus B on D, as this is by how much it has changed the capacitance of this system. So let's consider what happens when we put a non-conducting material between the two plates. So here we have our two plates. We've got a positive plate and a negative plate, and so electric field lines going down like this. Now what happens will depend on if we put a polar or a non-polar material in there. If we put a polar material in there, then the molecules are going to align to the field line so that we have a negative polarity at the top and a positive polarity down the bottom. They'll move as much as they can to align to the field like this. So polar molecules will try and align to the electric field. Now let's imagine putting a non-polar material in there. Such as polystyrene, which you'll be investigating in the lab. When you put non-polar materials into an electric field, you can actually get an induced polarity. So say we had a nice symmetric molecule like, say, carbon dioxide. If you put it in an electric field so that you've got a positive electric field here and a negative electric field here, the electrons will actually rearrange themselves so that they're slightly closer to this end here. So we'll end up with the electrons here and a more positive charge down here. So for non-polar molecules, we get an induced polarity. So effectively the same thing happens. They'll align up to the field like this so that they have a slightly negative charge up here and positive down here. So this is much like happened when we put the metal in, though not as extreme, as there was no electric field inside the metal here. There is a small electric field inside our dielectric. The size of the electric field will depend on the exact material that we use. So let's write an expression for the electric field between the plates. The electric field between the plates is now the electric field without the dielectric minus the induced electric field, which will oppose the applied electric field. So this will be given by the original electric field divided by kappa. This is how we define kappa, the dielectric constant. It's the amount that the electric field between the plates is reduced by that specific dielectric. So it depends on the material. So we can see if the electric field is reduced, the voltage is also going to be reduced. The new voltage difference between the plates will be given by 1 over kappa times the initial voltage difference between the plates. And since the capacitance is equal to Q over delta V, the capacitance will be increased by this factor kappa. So it will be kappa times the original capacitance. Let's consider what happens now when we put an electric dipole in an electric field. Okay, so now what we're going to consider is putting an electric dipole in an electric field. Now you may remember from the tutorial problems that an electric dipole consists of two charges, plus Q and minus Q, separated by a distance of 2a. Now we're going to define something called the electric dipole moment. The electric dipole moment is given the symbol little p and is equal to 2aq in the direction from minus q to plus q. So in this direction, And now consider that we apply an electric field in this case. So let's draw the electric field lines in red here, some constant electric field like this. And the question is, well, what happens to the dipole in this case? Well, force-wise, F is equal to EQ. And this is a dipole, so these are actually attached to each other. So when this negative charge feels a force, this positive charge feels an opposite force. So this tells us that the total force is 0. And so there is no net force acting on this dipole. However, there is a net torque. Remember that torque is equal to R cross F. In this case, both these charges we can consider as a distance A from the center. And so the distance R is equal to A, and F, we know that the force felt by each of these is equal to EQ, where E is the electric field. So this is AEQ, and then because it's a cross product, we've got a sine theta in there. So AEQ sine theta gives the torque on one of these charges. Now, because of these opposite signs, both of these charges are going to try and get it to rotate in the same direction in the electric field. So this positive charge is going to feel a torque trying to get it to turn that way, and this negative charge is going to feel a torque trying to get it to turn that way. So the torque is out of the screen in both these cases. And so the torques actually add together, and the net torque is equal to 2AEQ sine theta. And so we can write the torque as P cross E in this case, because P is just equal to the 2AQ, and the E is the electric field, and then the sine theta goes into this cross product here. So the torque is equal to P cross E. And now there is energy associated with this. We know that the work done is equal to the force times the distance, but we also have work done when we have a turning force or a torque, and the work done by a torque is equal to torque times d theta. And so we know that the work done when we put a dipole in an electric field, now this work, any work that we do on it, is going to result in energy being stored in our electric dipole. So it's going to result in a change in the potential energy of that dipole. So UF minus UI, the change in potential, will be equal to the integral from the initial angle to the final angle of the torque, which is here. We can write it as PE sine theta to get rid of that cross product, and then d theta. Now, the dipole and the electric field are constant, the dipole moment and the electric field, and so we've got the integral of sine theta d theta, and so this is equal to PE minus cos theta, and the limits were from the initial angle to the final angle, so this is equal to PE. And now to get rid of this negative sign, we'll just do them in the reverse order: cos theta initial minus cos theta final. And now by convention, we tend to take the initial angle as 90 degrees. So cos of 90 is equal to 0. And so by convention, we usually say that the potential stored in this way is equal to PE cos theta F. And we've got the negative sign here. So this term's 0, and then we've got this negative sign here. So we can write this as minus P dot E, where P is the electric dipole, E is the electric field, and we've replaced this cos F now with the dot product between these two vectors. And so polar molecules have a permanent dipole moment. So this P is non-zero permanently or polar molecules. Let's use this to solve a problem now. So the problem is the water molecule has an electric dipole moment, so P of 6.3 times 10 to the minus 30 coulombs meters. And we have 10 to the 21 molecules. And they're all orientated in the direction of an electric field with a magnitude E is equal to 2.5 times 10 to the 5 newtons per coulomb. And we're asked how much work is required to rotate the dipoles from an orientation of theta is equal to 0. So theta initial is equal to 0 to 1 in which all the moments are perpendicular to the field. And so the final is equal to 90 degrees. And so we can use U is equal to minus P dot E. Okay, so UF minus UI, which is the work done, is just minus PE cos theta final minus PE cos theta initial, just substituting into this equation here. And we have that theta final is equal to 90 degrees. So cos of 90 is 0, so this term is 0, and this cos theta initial, this is 1. This should be a minus minus. So we end up with this as a plus, so this is equal to PE. And so this is equal to 6.3 times 10 to the minus 30 times the electric field, which is 2.5 times 10 to the 5. Now, this will give us the work done per molecule, but we have 10 to the 21 molecules, so we need to times that by 10 to the 21 to get the total work done, which is equal to 1.573 times 10 to the minus 3 joules. And so we should just give this to two significant figures, as everything else is to two significant figures. So that's 1.6 times 10 to the minus 3 joules. Let's now consider what happens when we put capacitors in parallel and series. Parallel first. So here we've got capacitor 2, here we've got capacitor 1, and they're in parallel across a voltage source like this. Now, as they're in parallel, they're joined by the same wire here, so they've got the same voltage difference across them. So delta V is the same across both capacitors. So what we want to know is what equivalent capacitance could we replace C1 and C2 with. Find C equivalent that could replace C1 and C2. Well, we know that the total voltage difference across these two capacitors will still be delta V, and if we've got a charge plus Q2 on this plate and plus Q1 on this plate, minus Q2 on this plate and minus Q1 on this plate, the total charge on this side is going to be Q1 plus Q2. So Q equivalent will have to be equal to Q1 plus Q2. The plate would have to have that total charge on it, and delta V will just be delta V. So this tells us that the equivalent capacitance is equal to the equivalent charge over delta V, which is equal to Q1 on delta V plus Q2 on delta V, which is equal to C1 plus C2. So if we want to replace C1 and C2 with an equivalent capacitance in parallel, we just replace them with a capacitance equal to C1 plus C2. Now let's consider what happens when we place capacitors in series. So here's C1, here's C2. Now let's initially consider the case where we don't have any power supply down here. So I think you can see that this wire here with these two plates is going to be neutral. There's no charge on that. Now we place the power supply down here. So this plate becomes positive and this plate becomes negative here. Now there is no way for current to flow across this plate. So the charge on this section of the circuit here, let me just put it in a rectangle for you, has not changed. This is neutral. So we've got plus Q1 on this plate and minus Q2 on this plate. And so on this plate we'll have minus Q1 and on this plate we'll have plus Q2. And because this is neutral, I think you can see that Q1 is going to equal Q2. So now the question is, what equivalent capacitance can we replace C1 and C2 with? So Q equivalent, the charge on each of the equivalent capacitor's plate is going to have to equal Q1 and it equals Q2. The voltage difference, this one will have a voltage difference V1 across it and this one V2. So the voltage difference across the equivalent capacitor will be V1 plus V2. So now the equivalent capacitance will be equal to Q equivalent over delta V equivalent, which is equal to Q1 or Q2 over delta V1 plus delta V2. Now to make this easier to solve, let's write 1 on C equivalent is equal to delta V1, and this is on Q1, plus delta V2. Now Q1 is the same as Q2, so let's write Q2 here. And so this is equal to 1 on C1 plus 1 on C2, which is the same form as for resistors in parallel. So that's how we work out the equivalent capacitance when the capacitors are placed in series. What we're going to look at now is how much energy can be stored in a capacitor. Capacitors are usually used in circuits to store charge and hence energy. As we charge up the capacitor, we need to move little charges from the negative plate to the positive plate. The work required to move charge dQ is equal to the voltage difference between the two plates times the charge dQ. For a capacitor, which has constant capacitance, delta V is equal to Q over C, where this is the capacitance. So this is how much work we have to do to move a little charge dQ from this plate to this plate while there is a charge Q on the two plates. So to work out the total amount of work we need to do to charge this capacitor up to a total charge capital Q, we'll need to integrate this over that total charge. So we have that the work done is equal to the integral of Q on C dQ, and this charge is going from 0 up to capital Q, the total charge. And doing this integral, we end up with 1 on C times Q squared on 2, evaluated at capital Q and 0. So you can see this is going to be capital Q squared over 2C, or a half Q squared on C. So the energy stored in a capacitor is given by a half Q squared on C. Now, we may want to represent the energy stored in terms of the capacitance and the voltage. So in that case, we want to get rid of the charge. The charge on a capacitor using C is equal to Q over delta V is equal to C delta V. So that's squared on C, and you can see this will be a half C delta V squared. So this is another form of the energy equation. Another way we can write it is to now get rid of the capacitance. So we've got a half Q over delta V times delta V squared. So this is equal to a half Q delta V. So we've got three ways, 1, 2, or 3, to write the energy stored on a capacitor. Now, one other thing we should know is if we charge a capacitor up and we charge it up with a constant current, then Q, the charge, will equal the current times the time. So we can write that the capacitance is equal to Q, which is the current times the time, over delta V. And if this is a constant current and a constant capacitance, then you can see that you're going to have a straight line on the graph of voltage versus time. The gradient of this graph, delta V over T, will be equal to I over C. So you'll be using this relationship in the lab where you are looking at series and parallel capacitors. Now we're going to have a look at a couple of examples. In the first example, we have two capacitors C1 and C2, where C1 is larger than C2, and they're charged to the same initial potential difference, delta VI. The charged capacitors are removed from the battery and their plates are connected with opposite polarity. And part A says find the potential difference across the two capacitors after they are connected in parallel. Okay, so we're connecting them with opposite polarity. So here's C1, positive plate, negative plate. Here's C2, negative plate, positive plate. And we connect them up like this. Now, initially, we've got delta VI here and delta VI here. That's before we close this switch. When we close this switch, the charges will rearrange and we'll end up with delta VF between these two. So now what we're going to need to do is work out the charges and use those charges to calculate our final voltage. So let's look at the charges here. The total charge on this part of the circuit will be the same as the total charge on that part of the circuit over here, because no charge is being moved across the two plates. So let's start by working out the initial charge on both these plates. We know that C is equal to Q over delta V, so that tells us that Q1 is equal to C1 delta VI and Q2 is equal to C2 delta VI. So here we've got plus C1 delta VI and here we've got minus C2 delta VI. Now once this has been shut, these charges are allowed to move. So they're going to move to try and cancel each other out. So the total charge will be equal to C1 delta VI minus C2 delta VI. So this is C1 minus C2 delta VI. So that's the charge on these two capacitor plates after the switch has been closed. Now we can consider these two to be capacitors in parallel. So we know that the total capacitance is equal to C1 plus C2 in parallel, and we've now got the total charge across these two plates. So we can use that to get our total voltage or our final voltage. So we've got that our final voltage is equal to the total charge over the total capacitance. And so this is equal to C1 minus C2 delta VI over C1 plus C2. So that there gives us our final voltage. Now part B of the question says find the total energy stored in the capacitors before they are connected together and afterwards. Okay, so before we've got that our total energy is equal to, we'll just be using the formula E is equal to a half C delta V squared, and before we've got the two capacitors, so we just add together the contributions from both capacitors. So we've got a half C1 delta VI squared plus a half C2 delta V2 VI squared. So we can write this as a half C1 plus C2 delta VI squared. Now afterwards, We've now got the voltage difference across each of the capacitors, and we've got the capacitance of each of the capacitors. So we've got a half C1, and then the voltage difference is C1 minus C2 over C1 plus C2 squared delta VI squared plus a half C2 C1 minus C2 over C1 plus C2 squared delta VI squared. So we can write this as a half. We'll have C1 plus C2, C1 minus C2 over C1 plus C2 squared delta VI squared. So you can see the half C1 plus C2 delta VI squared is equal to the initial energy. So we can write this as U initial. So this is equal to U initial, where this is equal to the potential final energy, times C1 minus C2 over C1 plus C2 squared. Now, as C1's bigger than C2 and capacitance is always positive, this is going to be some number between 0 and 1. So some energy has been lost. The final energy is smaller than the initial energy. We would expect that because the charges will redistribute themselves to their lowest energy state. So this energy will be generally lost in the form of electromagnetic radiation. One more example. This example was in the 2010 1231 paper. Suppose you have two 3000 farad capacitors. So C is equal to 3000 farads. And we have a battery with a voltage difference of 120 volts across it. Part A of the question says calculate the total energy stored in both capacitors if they are connected in series across the battery. Draw a schematic diagram showing how the capacitors are connected to the battery. Okay, so we're just showing that we know how to connect capacitors in series. So in series, they look like this. So we've got C1, C2 with the same capacitance. Now we're asked to calculate the total energy. The total energy is equal to a half C delta V squared, and we're going to need to add the capacitances and the voltages for these two capacitors to get the total energy. So let's just have a look at the voltages. This is 120 volts, and then because C1 is equal to C2, this will have a 60 volts voltage drop across it, and this one will also be 60 volts. So U total will equal a half times 3000 times 60 squared plus a half times 3000 times 60 squared, one for each of those capacitors, which will give us 1.08 times 10 to the 7 joules is stored in that case. Now part B of the question says calculate the total energy stored in both capacitors if they are connected in parallel across the battery. So here we've got C1, here we've got C2, and here we've got our battery. So our voltage difference across both of these is now 120 volts. So we've got that our total energy stored in this case is equal to a half times 3000, that's the capacitance of this capacitor, times 120 squared, that's the voltage difference across this capacitor. Now we have to add in the energy stored in this capacitor, which is the same thing, a half times 3000 times 120 squared. Solving that, we end up with 4.32 times 10 to the 7 joules, so 4 times as big as this one. Now part C of the question says, now charge both capacitors to 120 volts, then join their two positive terminals together. Okay, so let's do an initial picture. So we've charged them both to 120 volts. We've connected the positive to the positive and the negative to the negative. Right, and we've connected the negative terminals across the battery. So we haven't closed this switch yet, but we've got our battery in here. Now the question says, draw a schematic diagram showing how the capacitors are connected to the battery and the voltages on all the components just prior to the final connection being made. Okay, and the voltage difference across the battery is 120 volts. So there, we've done that part. After the final connection is made, the capacitors will be in series with the battery and the current will flow until a new equilibrium is reached. Calculate the final voltage across each capacitor and the total energy stored in both capacitors. Okay, so now afterwards, we've got our two capacitors and we've got our battery here. Now our battery is now connected to these and it has a potential difference of 120 volts across it, which means that there must be a voltage difference between these two capacitors of 120 volts. So let's write this as the final voltage for capacitor 1 and we'll write this one as the final voltage for capacitor 2. We know that 120 is equal to the final voltage for capacitor 1 plus the final voltage across capacitor 2. Let's call that equation 1. What we're going to consider now is the charges. So let's consider the charges on this part of the circuit. There's nothing adding or removing charges from this part of the circuit once the switch is closed. So the charge over here has to be the same as the charge over here. So this is our capacitor 1, so we'll call this Q1 initial, this is Q2 initial, and here we have Q1 final and Q2 final. Now in this case, now that we've got the battery connected, this is forcing this plate to be positive and this one to be negative. So here we have a negative plate and here we have a positive plate. So we can write Q1 initial plus Q2 initial is equal to, here we've got Q2 final, that's a positive charge, but Q1 final is going to be a negative charge because that's a negative plate. So we've got Q1 final there. Now what we want to do is we want to be able to solve these two equations simultaneously. So what we're going to have to do is, rather than write these in terms of charges, we'll write them in terms of capacitances and voltages. We know that C is equal to Q on delta V, so that Q is equal to C delta V. So this is C delta VI, because that's the initial voltage across this capacitor plate, plus C delta VI is equal to, now final, we've got C delta V1 final, 2 final, sorry, that's the second capacitor, minus C delta V2 1 final, that's the first capacitor. So C's, the capacitances are all the same, so they cancel out. So we've got 2 delta VI is equal to delta V2F minus delta V1F. So this is our second simultaneous equation. So what we can do now is we know that the initial voltage is 120 volts. That's what we're told over here. So we've got 240 is equal to delta V2F minus delta V1F. So we can rearrange this to give delta V2F is equal to 240 plus delta V1F. And then substituting this back into equation 1, we've got 120 is equal to delta V1F plus 240 plus delta V1F, which tells us that minus 120 is equal to 2 delta V1F, so delta V1F is equal to minus 60 volts. Okay, let's just make a little bit more room because we don't want to lose this yet. So now we've got the final voltage across the capacitor 1, they have to add to give 120, so that tells us that the final voltage across the second capacitor has to be 180 volts. And finally, the question asks us to calculate the total energy stored in both capacitors. So U is equal to a half CV squared, so let's just add it for the two capacitors. We've got a half C, which is 3000, that hasn't changed, times minus 60 squared plus a half times 3000 times 180 squared. Solving that on the calculator, we end up with 5.4 times 10 to the 7 joules is stored across the two capacitors. And that's the end of capacitors.